Okay, let's hope this works. All right, so do you have any guesses as to why we're learning procrastination?
Maybe because then in the future, when we're learning about actual study skills, we know how to deal with procrastination.
Yep, exactly. And there's another like slightly different reason, but you're on the right track. There's something else as well. But that is correct. There's another thing as well. Yes.
So you know like exactly what it is. So when you when you do it, you're like, oh, I'm procrastinating right now. So then you kind of know what like causes it and like how to stop it.
Exactly. And like that's super useful and it's a problem we all have right now, right? One like there's two other reasons. It's because like related to your point, this is a low-hanging fruit. It's something easier to fix, right? Not saying you're going to fix it right away, but the strategies that you can implement are a lot easier. So we always start with low-hanging fruits, even if they're not the most like it's like what's your favorite fruit? Okay, I'll say mine. That says mango, right? I think mango is one of my favorites. Let's say mango is what I want, but then the apple is something I also like, but it's a bit further down. So I'm gonna grab the apple first, then we'll grab the mango later, because it takes more effort. And that's just faster. Like I know it doesn't seem obvious because you want to do the thing that's most impactful first. Does the analogy make sense? Right? A mango is the thing that's better, but it's harder to reach. And although it might make sense, like for you to think, oh, let me just go for the thing that's the most useful. But it's not actually efficient from like a time perspective to do the harder things first. So you want to start with easier, smaller fixes. Then once you have those down, those harder fixes become easier, right? And another thing is, well, the study techniques I'm going to teach you later on are also difficult, inherently difficult, right? And when you face them, you will probably want to procrastinate, right? Because again, difficulty of the task is a factor that makes you procrastinate, right? But if you have some strategies to deal with procrastination, then you can actually do them. Does that make sense? Because there's no way around it. They will be tricky at the start. Although they'll save you so much time in the long run, they will be tricky at the start. Okay? So you just need to, so we just want to take all the low-hanging fruits out of the way first. Does that make sense? I know it seems counterintuitive because it didn't make sense to me at first. When I first was learning, like my intuition for like skill development was that you should make the biggest change first, the most useful one. But if you can't sustain it and if it's too overwhelming, there's no point. Might as well make the easiest changes first. Then those harder changes become easier once you're more competent at it, at the overall thing. So, procrastination. Well, procrastination, it's basically when you have a very hard task. And I remember our brain is wired for short term, right? Think back to like caveman times, right? We were just meant to survive for the next week. That's how our biology is, right? So whenever we have something that feels threatening, a very hard exam coming up, it feels threatening to us, although it isn't. But like to our brain, what's the word for it? Intrinsically, like inside our head, it sees it as a threat, right? It just is. So instead, what seems nice, instead your brain goes, oh, I have a threat. Let me just, instead try to be happy right now, let me just go on Instagram. Let me just play some games, right? But although rationally speaking, that doesn't make any sense because you still have the test coming up. You're not going to have to do anything about it, but it's not rational. Like we're not rational when we procrastinate. I'm not rational so when I'm procrastinating. No one is. And that's just the nature of it. But it's basically when something seems threatening. So instead of being rational and just sort of trying to deal with it, we try to avoid it and do other things. So here's the strategies to procrastination. Now, there's three major types of strategies. So, like what do you think are the ways, like general ways what general strategies for dealing with procrastination? You probably heard some online, and think about, just share whatever you guys know about dealing with procrastination. You probably heard some things online, for sure, right? Reward system. Reward system. Definitely one of them. Now, why do you think reward system works? Yep, exactly. And if you go even deeper,
Then you feel motivated to finish it.
oh, good connection. Increase motivation, right? We can increase motivation by increasing, sorry, the word for this would be, decreasing the barriers to entry to the task, right? This is a strategy that decreases the barriers to entry for a task. Having a reward system, right? And this is pretty good start. Any other strategies?
Doing the small tasks first. Ones that I did yesterday. Once you finish those tasks, you sort of feel in like flow.
No, definitely. That's very good point. So that's actually also called, when you have like some momentum for a task, you just want to finish it, right? It's sort of like everyone has a sort of internal desire to complete tasks. So once you start, it makes things a lot easier. So I think that sort of falls into this thing, which is just starting early with easy tasks, right? Like if you have an assignment due 4 weeks from now and you're super stressed, you know what you can do? Just literally take a read of it and just do probably the easiest question. And then have the other question in the back of your mind because you want to complete it now, right? Whereas if you have no idea about it, you just start stressing more about it, right? So these are things that are decreasing the barriers to entry to tasks. There's something, wait, am I recording yeah, let's hope it's recording this. So if we're decreasing the barriers to entry for a task, what else can be decreasing barriers to entries for a task? Take a look at your thing. So I think probably there's one something that's even more powerful than these two, because reward system's good, but think about it, our brain again it doesn't manage well with longer term things. So the reward is sort of it makes it easier, but it's still at the end of the task. And because it's at the end of the task, you still got to get through it, and you might be still not be motivated because you feel like, oh, I have to get through this. So there's something else you can do that's probably even more powerful than these two, which is listing tasks. Right? If you list the things down into like a list, now all of a sudden it's more tangible. The task is not this big scary thing, right? You just go, okay, let me just do question 1, question 3, or like when I do preparation for tutoring prep, I go, oh, let me just first research on this, then I do this, then I create this handout, then I create this. I have a list of tasks. All of a sudden it's less scary than just going tutoring prep, for example, right? So listing the task is also very powerful, right? And there's one more thing, bit unusual. This one is called minimum viable goals. Now, this is a very powerful technique for changing bad habits, right? Let's say we have, we like to use, whenever we start study, we tend to use our phone. Or like we don't feel like doing studying. Let's say you're watching TV right now, and then you need to study after. You want to go from watching TV to the study desk, essentially. And you just break it down into super, super small tasks. If you take a look at the last page, right? It literally says, so a chain of MVGs to move from the couch to the study desk, maybe. Take a single deep breath, right? Literally, very easy, super easy. The first thing you do, you're on the couch chilling. Take a deep breath. You reset. Then you might take a few more breaths, right? Then your next task is to stand up. I know it seems super, super like basic and silly, but like when we're in this state, think about it. We're not rational, right? We're at the couch. We're like, I want to watch more TV. You want to make it easy. So you break it down into super, super, super easy with it, right? And this technique is actually super powerful, right? Because MVGs, although they aren't like the be all and end all, they make it super easy to break down, break hard to break bad habits, right? So these are our 4 strategies to decrease the barriers to entry for tasks. Now there's other types of strategies. So think about it. Procrastination is like a battle of against distractions and trying to get the task done, right? You want to get rid of the distraction and then make the task easier. So these techniques make the task itself easier. What do you think is something similar then? If you want to decrease in the barriers to entry to task, what is another type of strategy to deal with procrastination? Scheduling. Oh, yes. Scheduling actually would be here as well. And scheduling is already using some of these techniques, right? We're listing tasks in our schedule. We're also sort of starting early because we sort of write down the task. So now we have a bit of anticipation for it. So scheduling is actually a very good point, but it still belongs here. But there's actually 2 other classes of strategies, which has smaller strategies in them. They weren't in the handout. So I want you to guess what those classes are. So here's the thing, right? Think of this graph. This is why procrastination happens. You have this distraction that's super easy to do. Then you have this task that's super hard to do, right? And the first strategy was to literally decrease the task's difficulty, right? Or the difficulty in our head, right? What's something that's similar we can do then on the other way? What's sort of the opposite thing we can do? Decrease distraction or make the distractions harder to do, right? Increase the barriers to entry for distractions, right? Exactly. So distractions. And honestly, this is probably the more powerful thing to do. So if we make the distractions harder to do, we won't do them. Again, remember, we're just doing an easy thing when we procrastinated, right? Of course, if you want to watch TV, and that's something you should do because that's your intention. But if your intention is to study and you have your phone next to you and you're getting distracted, it's because it's an easy out. So you want to make it so that it's harder. For example, I'll tell you something. Whenever I get cookies, right? If I leave the box out on the pantry, just on the table, and I walk past, I'm gonna grab one every time I walk past, right? What do you guys think? I don't know. Do you have something similar like that? If you have something in front of you, it's hard to resist it, right? So, do you know what I do now to avoid that? I put it away. Yeah, I put it in a cookie jar, and I put it in a cupboard. Then I never see it. So unless I really intentionally want to have cookies, which I do sometimes, then I'm not having cookies, right? So that's just an easy strategy. it just makes your environment more conducive. So really, the distractions is all about your environment. Now, what does this mean for studying? This could mean that you maybe charge your phone far away from your study desk, right? So for me, I always leave my phone charging downstairs, whereas my room and my study room is upstairs. So my phone's basically never with me when I'm studying, right? So it's just sort of, you got to tweak your environment to make it easier to make your distractions less available. So, but you got to know what the distractions are, right? So you can start with the easier strategy, which is to do a distraction cheat sheet, which is where you basically write, as you're doing a task, you have a little piece of paper next to you. You literally write down a distraction, and then you're trying to come up with a solution to deal with that distraction. And when we do that, we are in our rational brains working now. Now, all of a sudden, you want to come up with a solution, and you will. So you might feel like, oh, well, I have my YouTube open when I'm meant to study on my computer. So you might block YouTube in the time you study, right? So those are the sort of things. So for example, I like to watch Netflix, and that's something I know that I want to do. So what I have is, it's only available for me from 6 p.m. to like 10:45, whenever I like set it to sleep. So after that, I can't watch Netflix. So I've done the blocker on my computer. Like I've just changed it, like, you can get an online blocker for that, right? Because I want to do it, but then I know that once I start, I also want to like do it when I'm awake and like studying and stuff as well. So I've restricted myself to those hours so that I can do it consistently, so that I enjoy it, but then I don't overdo it, right? So that's a environmental change you can do. So based on these, what do you think? I want you to work on one strategy this week, at least one, but one's enough. If you want to do more, that's great. So when you're studying, doing homework this week, I want you to work on one. Which looks the most interesting to you? Which is the one that you want to do? And then you can work on that. It can be different for each. Like the whole class doesn't have to do one technique. It can be like, you choose environment, you choose the listing task or reward system. So which one do you guys want to do? Environment? Cool. Yep. Environment as well then. And what about you guys? Environment? Listing tasks. That's pretty good. Listing tasks. All right, cool. So we got a mix of those two. So some of my tips for environment would be, I think the cheat sheet's very good at the start. So because you don't know what the distractions are until you get to them exactly. Like, of course, you know some of them, so you can fix them right away. But then there might be more that come up when you're studying. So just have a little sheet next to you and just write them down whenever you come up, whenever you notice that you're distracted. And then once you write them down, come up with a solution to fix it. Does that make sense? So for you guys doing environment, that's my tips for you guys. And for you guys, how do you think you can implement this?
Before I start like a task, I just list them out and then plan it.
Yeah, exactly. And thing is, you don't have to follow it perfectly, but it just makes it help you start, right? And then once you start, you might realize you might want to do other stuff, and that's fine. But like, just do it at the start for the sake of making it easier. And on your schedule, you can do that on your schedule, right? Put on your schedule to listing tasks, right? Also, for scheduling, I have another tip that I've noticed recently, because I've changed up my scheduling a bit. If you want, you can try this. What I do now is, do you know, like, do you have a voice recording app on your phone, like voice memos or whatever it's on Android? You can vocally say your schedule to the voice memo, right? And that's faster than when you do it on Google Calendar. Then you can get the transcript of that. And if you have Gemini connects you to Google Calendar. You can tell Gemini, can you please put these tasks into my calendar? So you might be like, okay, today I'm gonna from 8 to 9, I'm gonna be doing this. From 9 to 4, I'm at school. From 4 to 5, I'm traveling home. From 5 to 6:30, I'm studying maths or whatever. Just say, you can say it a lot faster. I can literally do it, schedule in 2 minutes, right? Then once you have that, you can put it onto Gemini, because that's connected to Google. And then you can have your schedule set out from like, just with, like in 2 minutes. Then you're done in like 5 minutes with your main schedule. Then all you need to do is go to the actual calendar itself. Then you can like add more details. You can add specific details inside the task. It just becomes a lot faster. So if you want, you can give that a go for whoever's using Google Calendar. I've noticed that I've saved a lot of time from doing that, because before I spent about 20-30 minutes scheduling. Now it's like 10. And I still get the same detail because I spend 10 to 15 minutes, but I spend 5 minutes just with like getting the big skeleton down with my voice recording. Then I spend the next 10 just tweaking and like actually adding details like the specific tasks in there. Does that make sense? So yeah, I think give that a go if you want. Does that make sense? I think if you want to save time, that's very powerful. Okay, cool. Any final questions? Right, so yeah, and again, it's super important that you spend time at home implementing these, right? Not much point otherwise, but I know you guys are diligent, so you get them done. And with regard to pre-study, just keep it up. And like you don't have to do pre-study like on a new topic each time. If you have a topic that you pre-studied before, keep doing pre-study for that a little bit more if you're not learning anything new. Like, oh wait, you guys do like watching videos and things. Okay, that's fine. Keep that up. Yeah. Okay, now let's get to maths. It's already 9:50. Okay, so modular arithmetic. What do you guys remember from last time? Yeah, if I ask you, like, what's the most important concepts in modular arithmetic, what would they be?
N equals to mod n.
Yes, that's actually for the most fundamental concept. I guess what does that mean and why is that important?
It's congruent to be modular n. If we have same number divided by n.
Yeah. Can someone give me an example of two numbers that are congruent without looking at notes? We have the definition. Now we just need to come up with an example based on that definition.
I want to convert.
So it means they have the same remainder when you divide by that number. So if it's mod n, when you divide by n. You can just tell me two numbers and you can say like they're congruent in this modular. So I'm going to give you a wrong example here. I'm going to say 10 and 3 are congruent modulo 5. It's wrong, but that's how you can say it if you want. And if you're struggling, think about why you're struggling. And if you want to ask a question like, it's like, oh, I'm struggling with this, I'm happy to help out.
Two numbers, so if you do 7 and another number and then mod n, and they divide by 2, so they both have to have the same remainder.
Divided by n.
Divided by n.
Yeah. So you divide both by n, they have the same remainder. You can pick n.
I can't think of two numbers in mod n.
You can start from n if you want, and then find two numbers based on that. So everyone think. Even thinking here is worth it, even if you don't get to it.
Mod 3, 11, and 8.
Yes, and what's the remainder? That's a great example. It's 11 equals to 8 mod 3. Why is that? If you divide 8 by 3, well, you don't need to do long division. One digit. It's 2 with the remainder. What's the remainder? 2, right? Because 2 times 3 is 6. 8 minus 6 is 2. But 11 divided by 3. It's 3. Remainder 2. We only care about the remainder for the mod congruence. We don't care about what these numbers. Does that make sense? So that's an example of two numbers being congruent. Cool. Now can all of you come up with another example? And not 3. 3 is not allowed. Let's say n has to be at least 7. And the two numbers both have to be bigger than 20. By the way, for congruence, you do 3, let's say, equal sign with 3. See how I've got 3 horizontal lines instead of like 2 horizontal lines? So you just literally change this to like add another horizontal line. Yeah. You got one number, so you can find another number with the remainder. What's the remainder you look for? Do you want me to give you a shortcut? You did it. What's the other number?
34.
34, yeah. 4 remainder 6. Good. Cool. So we all know what remainder is, congruence is now. So you know like most of the what this definition means, right? It just means the same remainder when you divide by that number. But there's also an algebraic definition. That might seem weird at first. I know it was for me, but this is really powerful for deriving properties, right? So algebraic definition of A equals B mod n. And you can say both of them are maybe congruent to some R mod n, where like R is between 0 and n. Does that make sense? There's always like the remainder is between 0 and n, right? This is sort of the remainder they're congruent. So like A and B both have the same remainder, so they're congruent to this R. Does that make sense? So for example, you know when you said 11 is 8 mod 3, what would the R be? Yeah, so they're also both congruent to 2 mod 3. Cool. Does that make sense, what I've written down here? So A is equal to B mod n, and they're both congruent to some small remainder that's less than n. Because remainder is always less than n. What this means is algebraically, A is some kn plus r, and B is ln plus r. And k and l are whole numbers. It might not seem super shit. Actually, does it make sense? Right? It's just this bit is a whole number times n. So it's a multiple of n, right? Then you have the remainder. And actually, if you think about it, oh yeah. But first of all, any questions about this?
What's that in front of n? Like the
This is k and n. So this is just the letters k and n. So bad k. But it's just k and l are some whole numbers. We don't know what they are. So for example, I'll give you an example. 11 is, again, 11 is 8 mod 3. We were working with that example. How can you represent 11 and 8 in this way?
k times
Plus 2. And what's k? Because we know what 11 is, we can find k. K is
9. I mean 3.
3. Exactly. 3 times 3. So 3 is our k. Does that make sense? So we know k when we have an example, but like in general, we don't know what k is. That's why I wrote k as just some whole number. Does that make sense? And if you go to 8, what's that? Can someone else give me the breakdown of 8 into these components? So 11 is 3 times n, which is 3 times 3 plus 2.
2 plus 2.
Yep. So it's L or K would be 2 now. Cool. Makes sense? And like, think about why this leaves a remainder of R, right? If you divide this thing by n, this thing, kn divided by n would leave what? K. And then R divided by n, that's the remainder bit, because it's like R is this number smaller than n. So if you have 5 divided by 7, what's the remainder? Remainder? Cool. Think about it. 5 divided by 7. Not 7 divided by 5. 5 divided by 7. That's a fraction. Just think in remainders. It's a number between 0 and 7. 5. Whenever you have a number smaller than like the number you're dividing by, the remainder is just that number. because like 5 divided by 7, you have 0 sevens in there. The remainder is just the entire thing. Cool. So that's why this leaves the remainder of R, because this bit gets you like a 0 remainder. And that means the R must be the remainder because R is smaller than 7 or N. Cool. The point is every number, you can break it down this way. Now, you might not see why the point of it is right now, but just trust this definition for now. Actually, I'll tell you why this is useful later down the line, is because when we have these algebraic properties, to prove the algebraic property, you need this definition. So you need the algebraic definition to prove the algebraic property. Otherwise, it's just all sort of wishy-washy intuition. And intuition is pretty good, but having a proper proof is a lot nicer. Now, any questions about that? Cool. So now we'll see why this algebraic definition is super important. So let's go to the first property we're going to learn. We did touch on this last week a bit. Wait, sorry, I just don't trust the recording. No, it is still recording. So, is the voice on me? Yep, okay. So the property we're using here would be the first property, which says that A equals B mod N and C equals D mod N. The property says that A plus C equals B plus D mod N. Cool. These are things we know. And then you use these to get the property. Does that make sense? This seems a pretty trivial one, but if you have two numbers with the same remainder and you have another two numbers with the same remainder, you can add those two and they still leave the same remainder. So an example of this would be, we know that 52 is equal to 12 mod 10. Would you agree? Because the remainder would be 2. What about, can you give me two other numbers that are congruent mod 10? Any two. Any two. Don't have to be congruent to these two. Just two numbers that are congruent to each other. 51. Let's leave the same remainder when you divide by 10. The n has the same.
12 and 1,000.
Yep, anything. And it doesn't even have to be 2. It could be something else completely. You could have the remainder be 5. Does that make sense? I'm just trying to make sure that you understand that the other two numbers don't have to have the same remainder as these two. So just for that example, can you give me, just for the sake of that, can you give me an example where the two numbers have a remainder different from 2?
45 and 65.
45 and 65. Cool. And what would the remainder be here? Can someone else tell me? What's that? What's the remainder?
5.
Yeah. It's not a tricky question. I'm just asking. See you guys. Yeah. Cool. So according to this property, what's A, what's C? So let's apply the property. What would the properties tell you?
+52 plus 45 equals 12 plus 6.
Yep, exactly. Mod 10. And does that look right to you? Because what's 52 plus 45?
900.
Close, 90 something. 97. And 12 plus 65? 77. And do you think they're the same remainder mod 10? Yeah, right. They both leave the remainder of 7. Right, 10th easy to look at, right? So we've seen one example that it works. So do you guys trust that now? You shouldn't. You shouldn't trust something because it works once. You need it to work for everything, right? Like, what if I said A plus B is A is true? What if I tell you this is a property? And then I give you, oh, well, look, 2 plus 0 is 2. That works. Do you believe me? Should you? No, right? Because I'm lying. One example is not enough. Because then I can give you another example. Like, oh, well, but you can tell me, oh, 2 plus 3 is 5. That's not 2. That property doesn't work anymore. So one example is not enough. And in fact, there could be a million examples that works. But even if there's one that doesn't work, all of a sudden it's not a property. Property by definition works for all examples. So the only way to be fully trusted is to prove it. And here's where our algebraic definition comes in. Yep. So if A equals B mod n, and let's say they have the remainder R1 and these two have the remainder R2. What can you write A and B as? The remainder, there is some remainder, right? So we know it's some remainder. Just say it's R1 and R2. What can you write A as?
And remainder.
We want algebraic way. Like, do you remember the algebraic definitions? So instead of like remainder, just like an equation. Do you remember what the algebraic definition was? Try to recall.
Equals to whatever, like.
You can pick a letter if you don't know. That's fine.
And
R1 because I said it's R1. What about B?
A equals to Ln plus R1.
Yep. What about C and D? Can someone else tell me? The remainder is R2, by the way. First of all, this definition makes sense. I'm just applying the definition to these two numbers. So if we apply the definition to C and D, what does that tell you?
Equals to Xn plus R2 J Y n plus R2.
Yep, exactly. You just pick a random number because you don't know it, but you also want it to be a different number because otherwise you like have a relationship between these two numbers and you don't want that. You just want it to be any number. So yeah, it's very good that you picked something that's not K and L. So now we know that A and B in terms of this remainder bit. So now if you go to A plus C, what is that? In terms of these sort of definitions, these algebraic definitions.
N plus Xn plus R2.
Oh, is everyone following this? We sort of added these two, right? Yes, makes sense. And what happens? K plus X. I see. What can you do to this? Collect like terms. Which would those be? Oh, by the way, R1 and R2 are not related. They're like two different remainders. I do use R for like the fact that they're remainders, but R1 and R2 means they're different. But you are on the right track. The N's, Kn and Xn.
KXN.
close.
B plus X. Yeah.
So take a plus. Why is it like, the reason is, well, if you have 2x plus 3x, that's 2 plus 3x, that's 5x. It's not 2 times 3x. Does that make sense? We're just using the algebraic property, but in general. Cool. And it's good to do. We just, again, you're beginners to algebra, so it's fine to make mistakes early on. It's very good to make mistakes, just fix them as you go. And you also have, I'm going to do b plus d, that bit. If you do b plus d, you'll get L plus yn plus R1 plus R2. Cool. Now look at this. This bit is a multiple of n. So a plus c is just the two remainders added together. That's sort of the remainder bit, right? And so is this. So do you see how they both have the same remainder part? So when you divide these two by n, they'll leave the same remainder. Cool. That's why they have the same remainder, and therefore they are same number mod n. Any questions about that? Does that make logical sense? You know, if the remainder is like 3 and 4, or say it's 3 and 9 even, this is also 3 and 9, and let's say n is 10, right? You divide this thing by 10, this thing just cancel. There's no remainder with this bit, right? Because it's a perfect multiple of 10. But then you have 12 and 12, divide both by 10, remainder of 2. Any questions about that? Again, I'm not asking, like I said, it's bad to have questions. It's good if you have questions. And I want you to clarify them now if you have any questions. Do you have any questions? Okay. So, because again, this property is not the super useful one, but we're going to use this as sort of the foundation to learn about the more useful property, which is, again, with these exact numbers. You have, this is the second property that's more useful. And we'll see why it's useful soon. If A is equal to B mod n and C is equal to D mod n, then what this says is AC is equal to BD mod n. Okay, so now let's see an example of this. Let's go with the same numbers. Now let's go with easier numbers. We have 8 equals to 2 mod 3. And then let's do 4 is equal to 10 mod 3. What does this property say?
Times 4 is equal to 2 times 10.
It also says you can also always just swap these two. So you can 10 is also equal to 4 mod n. So you could also say 8 times 10 equals to 2 times 4. It doesn't matter the order, but both would be correct. So let's just stick with one. And then when we do this, what do we get? 8 times 4 is, yep, good. And then 2 times 10 is 20 mod 3. Do they have the same remainder mod n? And what is it? 2, right? 32 is divided by 3 would be 10 remainder 2. 20 divided by 3 would be 6 remainder 2. Cool. Any questions about that? Let's do a quick example where I want you to find, this is where it's super powerful, right? So this is the first property that has the proper use. Find following. Give me the remainder. Find remainder. When this divided by 7. And I really don't want you to multiply 47 by 93. I want you to find a shortcut. Think about how we can apply this property we just learned. Let's move this here so that you can see the exact property as well. Cool.
Wait, so both will be the same remainder, right?
No, it's one number. It's 47 times 93.
Oh.
I want you to find the remainder of that when you multiply those two. But you're not allowed to multiply 47 by 93. I know you can. So you're like, ugh. Think about how we can apply this property. Of course, we can do 47 times 93. I know that you can do that. But then you have to find that big number. And you also need to find the remainder of that big number. You have to do a long division on that big number. Is there a faster way? So I guess first of all, what mod are we working in? Mod 7, right? That's the first thing we need to notice. This is our first application, which is with this property, now we can find remainders faster. My hint for you, if you're stuck, what is there a number? Remember, we're working in mod 7. Is there a smaller number equivalent to both of these, mod 7? That we can find relatively easily. If you're tempted to actually multiply, I know that it's probably the fastest, like the easiest method, but once you get used to the modular method, it'll be a lot faster. And remember, every number is congruent to the remainder. Would you agree? Like, you know, if 12 is 5 mod 7, then 12 is congruent. Sorry, yeah, if 12 divided by 7 has a remainder of 5, That means 12 is congruent to 5 mod 7. For any number, you can find a congruence just by getting the remainder. There's always like plenty of numbers congruent to whatever number you give. All right, who's found numbers congruent to 47 and 93? I'll tell you right now as another hint. This is like your A, and this is like your C. You don't have the B and D. So you need to find the B and D first. Because look, then AC is 47 times 93. And that will be congruent to BD. Does this make the problem clearer? Anyone still stuck, or are you making progress? As long as you're doing something, that means you're making progress. So if you can find the B and D that are perhaps simple and nice, you're pretty close. Again, remember there's infinitely many numbers congruent to 47 mod 7, right? But picking a nice one, that's probably the best. What's the nicest number? 7. Is 70 congruent to 47? Oh, we want a remainder. Like we want another number with the same remainder. That's what congruent means, right? So what's like the simplest number? Actually, what's the remainder? You divide 47 by 7. 5, right? So we know the remainder is 5. If you do long division, you get it. If the remainder is 5, what's the simplest number congruent to 47? 5. And why do you want a simple number? Because look, 47 times 93 is a big number. But if it's congruent to some super small number, we can use this. We can find the remainder from that small number. Does that make sense? So if you do the same thing to find D, which I've written as C, I'll fix. What's the other remainder?
3.
Is it 3 for 93? Back yourself if you trust you're working out, you should back yourself. It's a battle between 2 and 3 right now. What's the remainder when you divide 93 by 7? Everyone should be able to do that, right? Yeah, 2. It's fine if you make an error, just need to do the process, which is 93 divided by 7, do long division, then get the remainder. Actually, does that process of finding a remainder for like easy number make sense? Just do long division, right? So 93 is congruent to 2. So 47 congruent to 5 mod 2. 93 is congruent to 2 mod 7, sorry. Then that means 47 times 93 is congruent to 5 times 2 mod 7. Agree? What's 5 times 2? 10 mod 7. But what's the remainder? You need to divide 10 by 7. 10 is bigger than 7. 3, right? Just 10 is 7 times 1 plus 3. So it's 3. Cool. Now I know that was not fast. So if you had if you had done multiplication, but it is faster when you get used to it, right? It's just like anything else, right? Like when you're learning a new technique, it might be a better technique, but if you're still a beginner, you might still be slower than like your old technique. Like for example, like let's say you've been running towards to get from like A to B, right? All of a sudden you get a horse. In the first 20 minutes, you don't know how to ride the horse. You're probably going to be slower than when you run. You're going to like fall down a lot, right? But then once you get good at riding a horse, you'll get there a lot faster, right? The same thing with new techniques. Like, can you see how this technique would be faster when you apply it more and more? Yes or no? I want you to be able to see it because you don't have to say yes just because I said it. Yes, right? But that doesn't mean you're faster at it right now. But you still work at it because you will get faster. And I want you to see that how you can get faster, right? It's just once you get used to it, this is definitely a faster technique. Just quickly get the remainder of 47 and 93. Then you just use it to find the overall remainder of the product. Okay, so what I'm going to do is going to give you a 5-minute break, and then we'll come back and do a bit more work. And we'll prove this property as well with algebra. By the way, is it cold for you guys? I can turn the heater on. Do not disturb on. It is on. By the way, do you guys need to leave early today? Or
Yeah, we just have to leave 10,
okay,
like
yep.
10:50.
Okay, cool. Let's get started again. Also, for next time, if you guys do feel cold early on, please let me know. Like, I can forget sometimes when I'm teaching. I'm always happy to turn the just heater on. Yeah, I'll try to remember as well, but again, I can forget. So now we know what the second property is. We also know how to use it, right? But I guess, do we trust the property? Trust it a little bit because you've seen it work a bit, but again, not fully, because examples can be misleading, right? Like, and that's why maths is tricky, because you need to prove it properly, thoroughly for every example. And to do that, you got to work with general examples. So let's prove this property. And now here the algebra gets a little bit tricky, but it's still within our reach. Actually going to be very good practice for the types of things we'll see in our next topic, which is going to be quadratics. So we can actually see a quadratic expression here, but we can still get it because to get to that expression, we'll be using properties, things we know. So we're not using any advanced quadratics knowledge that you'll learn later, but it will be quadratic. So here's the proof. Well, what do you think we start off with? General proof. Any guesses as to how we're going to start this proof? Think back to how we proved the other one. How do we prove the addition property? Yeah, what's the word for it? Yeah, the algebraic definition. You use the exact same thing, and look, it's the same exact starting conditions, right? A is B mod n, C is D mod n. We're gonna do different things with it. So now that we have this, what should we do? Right? We know this based on the algebraic definition. And let me actually move this away so that I can set this up next to each other. So A is Kn plus R1 and B is Ln plus R2. Sorry, R1 as well. C is Xn plus R2 and D is Yn plus R2. Now, anyone have any doubts about this, or does this definition make sense? I've just applied the algebraic definition, right? So based on this, what should we do? So into the equation, or to this one. Is that what we want to do right now? What's the reason for getting this algebraic definition?
So that we know it's 100% correct.
Yes, that's like the big picture, but like if you go more specific, what makes this more powerful than like just the A and the C? And if we look back to what we did here, we just added these because this gives us more insight into what this number is, right? So if we go here, AC, right? We can just plug in the definition. Makes sense? Now, I'm going to ask you guys to do this bit because it's good practice for future. Can you expand out this expression? And which property do you use? Tell me, like, in words, how you're going to use this. Do it. Not like actual maths behind it. What's the process you use to expand it? Yep. Algebra, which property though?
Multiplying it.
Yep. But how are you going to multiply? Because it's not a number. It's like a weird expression, right?
Like,
Distributive. And you might have heard of the acronym FOIL. First pair, outer pair, inner pair, last pair. But it's just distributive property. You don't need, if you understand distributive property, you don't need to use this. But you just multiply each like this as two pairs of two. So you just multiply these 4 terms. You multiply these 4 terms. And what do you get? Does it make sense how you multiply just like this? You have like 2 sums within each product. So you just do each pair of terms and multiply those. Who is unfamiliar with this property? Be honest. Please be honest. Yes. Thank you. I'm going to give you a visual proof of that soon. But if you are unfamiliar with it, I just want you to do it. Just do this, multiply these 2 first, then these 2.
Oh, no, I'm familiar with that. I just like don't know how to do these.
Okay. Right. So in this case, just multiply like terms together. So you don't need to like get a number, but like you have kn times xn.
Xn squared.
Yes. That's just that first bit, kxn squared. Leave the numbers that are different separate, and the numbers that are the same, you can like square them or whatever. And again, remember k and x are all whole numbers by definition. Who's not familiar with the actual FOIL thing though? Do you understand why it works? Yes. Okay. What about you, Tanuki? Do you want me to go through it? I can go through it. I'm happy to go through it.
I just don't know how to like expand
So yeah, in that case, just same advice, right? It's just like you have kn times xn. Just leave the different letters separate. And then like if you have 2 n's, n times n, that's n squared. Just leave this like different letters separate from each other. But then if you have 2 of the same letter multiplying, that's sort of squaring, right? You just
4 main dot 1 and 2 is it just 2? One time.
all right. So this notation is a bit weird, but think of these as different letters. I know they're both R, but it's R1, R2. It's not like R1, R squared. It's at the bottom, right? So it's substitute. It just means they're different variables completely. I could have said R and S instead of R1, R2, but pretend they're different letters. It's just notation, right? So if you expand, first term is kxn squared. Second term would be kn r2. First times outer, last one. Then r1 xn, I'm going to do xn r1, because remember, order doesn't matter. And then finally, I'm going to do r1 r2. Cool? And now we got the expansion. We need to make an observation from this expansion. What's the key observation? And I'm actually going to do the exact same thing to BD. Maybe that might help you with the observation. You'll get LYN squared plus LR2N plus YR1N plus R1R2. Okay. Same thing, same process repeated. You can copy this down. What is the key observation we need to make here for the proof? Why is it the same? Again, we're trying to just prove that they're the same remainder, right? That's our goal. Keep that goal in mind. What's the bit that's the same both? Thing is, R1, R2 is not the remainder. It might be too big. But it's R1, R2 is the bit that's common, right? The equation, but the equation not like, they're the same process we did, but they're not the same expression, right? This whole expression, not this expression. They can't be, otherwise, like they're not the same. Otherwise, they're the same numbers. So, common bit though is the R1, R2. That doesn't mean they're the remainder, but that is a common bit. And this bit's separate. But is there an observation we can make about this bit? There is a very key observation we need to make about this bit. What does all three terms have? N. And if all three terms have N, that means? Cause, and what did you say? I mean, what does mod mean? You're on the right track. You're both on the right track. What's that?
Congruent.
Yes. Or if we can give it simpler, before we can go to congruent to N, they are congruent to something. But what's even more simpler, if N is common to all of them, what does that tell us? Forget about mod, forget about, if I told you all these numbers have N in them as a factor.
They don't have the same remainder.
Multiple of N. They're all multiples of N. That means the whole sum is a multiple of N. If you want, you can take out an N as a factor. But the key thing is, actually, yeah, sorry, I sort of dismissed your point a bit too early, but I think you're on the right track. But it's the key observation from the fact that it's a factor is that it's a multiple. These three are all multiples of N. So yeah, I think you're very close actually, right? Because N is a factor of all three of them. But that means this sum is a multiple of N. And that's the thing we need. Why do we need that? Because agree, I'm just distributing. Do you follow me here? Makes sense what I've done here? Just take out N from all of them. Take out a common factor. If it doesn't make sense, let me know. What I've done is, if I took out N, that means I've divided everything here by N. And then I brought it outside. So kxn squared divided by N is just kxn. Knr2 divided by N is just kr2 because N goes away. And then what happens to this when I divide by N? This goes away. And that's why it's just xl. Cool. I know it's probably not something you're too familiar with. But again, I don't want you to be too familiar. I just want you to follow along. And we'll learn this in more depth when we get to quadratics. You'll be like expert at this stuff later on. But for now, it's fine to feel uncomfortable, right? Because again, you haven't been taught this yet even. But the logic you should be able to follow. That's the key thing. So, and you can do the exact same thing for the BD, right? Take out the n. It's a factor. Cool. And that means n is a factor of this. That means if I divide by n, what's the remainder of this part?
Insert the brackets.
I'm dividing like this entire number.
It would just be the brackets without it.
Is it the brackets though? I'm asking the remainder, not the quotient. Yeah, the quotient would be the thing without the n. What's the remainder of this? Any guesses? A number that's a multiple of n. I say, what's 14? If I divide, what's 14 mod 7? What's the remainder when I divide 14 by 7? 0. Everyone, don't confuse quotient and remainder. It's just fine to make a mistake. Do you see the difference? It's, again, don't worry about making a mistake, but understand what's the difference. So what's the difference? What's that? What's the number you said?
2.
Which is the
A quotient.
quotient. So we want the remainder here. So we're always working with remainders in this section. Again, you're not wrong because you said the quotient, but it's for the remainder, it's 0. Does that make sense? But the point is, whenever a number is, oh, you guys need to leave, right? Yes. No worries. Yeah, just watch the last bit of recording for this. But whenever the number is a multiple of n, you divide by n, the remainder is just 0. Right? Make sense? So the remainder is 0 for this bit. That means the remainder can only come from this section. Right? So that means AC is congruent to the remainder 1 times remainder 2. Because this bit, there's nothing to the remainder. This bit has a 0 remainder. Yes. And that means, so is BD, right? Same logic. They're both congruent to the same thing. That means they are congruent to each other. And that's our proof done. Cool. Again, I'm not expecting you guys to recreate this proof because a lot of the ideas here are foreign and like that's, I guess, part of it. You can't really avoid that. But do you follow the logic is the point I'm trying to, yes. Since you follow logic, you can sort of trust this. And again, if you want to challenge yourself, try to recreate this. Because if you can try to recreate this proof at home, you learn a lot of important skills that you'll use later on in quadratics, right? This is, we've done a bit of expanding and factorizing, which are super powerful in quadratics. So before we finish, now we know the property, we know the proof for it. Just to recap, what's a use case for this property? Where can we use this property? If we've seen a problem, we used it. That's the use case. What was the problem? Yeah, find the remainder of big numbers. Right? You can find the smaller congruences. Then you can find the remainder of those smaller congruences multiplied together. And when you do that, you'll get the remainder a lot faster. Do you see this? So we found 47 times 93 divided by 7. The remainder, not the actual number. Again, for the actual number, you can't do much. You just do the multiplication. But for the remainder, there's shortcuts like this. Cool. Okay. Any final questions about this? Let's take a look at a problem. Oh, okay. This one is a bit tricky. But it's the same idea, nothing new. For part A at least. By the way, natural number just means positive integer. It's a whole number that's positive that you can count. That's why it's natural. Things you can see in the real world. Because you can't see zero and you can't see negatives. They're still integers. But natural is considered things you can physically, tangibly see. That's why. Positive integers. Convert this information into something more useful algebraically or modular, like with a modular expression. And you can get these. So what it's saying is you have two numbers and you divide them by 12. One of them has a remainder of 5. The other one has a remainder of 9. Yep, makes sense. Yep.
So do you just find the two numbers, or do you have to answer the question?
Well, you can't find the two numbers. There's like infinitely many numbers, right? Like, 17, 29, 41, 53, 65, 77. Every single one of those numbers leaves a remainder of 5. But the point is, it doesn't matter what the number is. They have the same remainder. That's why you can use. And that comes from a property we just learned.
So product means you should times it.
Yep, times the two numbers. Again, you're not going to know the numbers. You can't know the numbers. It can be any number. As long as it satisfies the property stated in the question. Again, which property do you think we're going to use here?
Second.
Just going to figure out how to set it up, right? Because it's a product, so it must come in at some point. Also, the multiple of n's just the first bit, not this bit.
Oh.
Because it's n in all of these two. That's why it's multiple.
Wow.
You see that? Yes. You can just like change the brackets to this. Keep these two. The first three, all of them, those three.
So then when you're doing A, it's like 5 and 9 being the remainders.
Yep.
But doesn't it say? It's one remainder when divided by 12, and then it says divided by 12, the remainder is 5.
When their product, the product of the two numbers.
So it's different.
Yeah, so it's not like the numbers itself.
So
Fine.
5 and 9 are the separate remainders.
So, yep, first number, right? A, you divide by 12, remainder of 5. You have second number B, divide by 12, R equals 9. Question A asks you is, if you multiply A and B together, what's the remainder? It's the remainder of A times B, not them separately. Yep, A times B divided by 12. I don't want to give you too much hints. That's why I didn't give you the proper notation. But I want to set up that notation. And I'll give you hints soon. Do you understand the question now? So for A, it's the two numbers that we don't know multiplied together. It's asking us the remainder of that product, you divide that by 12. Probably want to set up a congruence. A equals something mod 12, something equals something mod 12. Is that, I mean, think back to how you did the first question. Wait. Is this question any different from the first question you saw? Not really, right? It's just a bit more hidden. It's the same exact question. So you're pretty close. You've got A is equal to 5 mod what? 12. What's the other one you want? 7. Then what do you do from there? What's A equal to? And is A and C your two numbers that you don't know? What's it equal to mod 12? Again, there's plenty of numbers, but if you even know one, that's like. So what do you need to find? Yes. Which one would that be? A and C or B and D? And what do you define A and C as? Oh, no, but A, what's like your original numbers? You can choose. Is that A and C or B and D? A, let's say A and C, right? Then we need to find B and D are some numbers congruent. Do you know any number congruent to A and C? Not sure. But do you need to know? You've got some information about it. The remainder is 5. How are you going? Yes, okay. So then, oh, have you got an answer? Put the answer somewhere. Just happen. I can see it. but let's reset. A is equal to 5 mod 12, C is 9 mod 12, right? That's because they're the remainders. And what are we trying to find? The remainder of? Whether then what? What's the operation on multiply? So it's A times C, right? And again, we can't find it directly because we don't know what AC is. But what is it equal to? What is it congruent to? Yeah, AC is equal to 45 mod 12. So if you know the remainder of 45, you also know the remainder of AC.
So it's the remainder 9.
Yeah. Makes sense. Right. But I want you to understand why. Do you understand why?
Because A times C, and it has to you times that and then divide that by 12.
Yes. No, just A. Just A divided by 12 is 5. So why is it 45? Where does this come from? Where does it 9 times 5 come? Yep, 2 remainders.
Yeah.
And which property are you going to use using that? This I'll explain. So I'll go back to this one. Previously, so if I take a look at the previous page, you have the other question. So, yes, this one. 47 and 93. 47 was 5. 93 was probably got easier to 2. Right, so yeah. Wait, you meant to go down to 5 and 2. Wait, so you got it here, right? 5 and 2. It's actually converted to 5 and 2 here. You can just change these two numbers to 5 and 2. Then if you just apply this property directly, 47 is equal to 5, 93 is equal to 2. A and C and B and D, yeah. And if A is congruent to C and B is congruent to D, oh no, other way. If A is congruent to B and C is congruent to D, A times C is congruent to B times D. So we have the congruence here. Yeah, this is your B, C and D. These are simple numbers. So A times C is congruent to this bit.
So is it like the same?
Yeah.
So do I keep dividing still?
No. So you got A and C, right? Yeah. That means A times C is congruent to these two multiplied together.
Oh, okay.
And these two is a tangible number, we know, right? Yeah. If you just find the remainder of these two, that's also the remainder of these two multiplied together.
It's just like this one. It's to like this part is this equal to the remainders. So equal to A and C.
B and D.
Oh,
A and C are these numbers.
okay.
So you can replace 75 with 5 here. Because yeah, these are correct, but they make our life harder because they're bigger. We just pick the simplest two numbers here. You see how our life becomes easier. So I think you should change this question to that as well at home. Yeah. You can do it now quickly if you want. And then you just directly apply the property. That 47 times 93 is 5 times 2, 17. And the same thing you're doing here. Cool. All right. It's 11:07. We'll wrap it up there. Do you want to do a Kahoot?
Chef have to go quickly. Chef have to go quickly.
Okay. Yeah, up to you guys. What do you guys think? If you want, you can check, or if not, if you want to have, I'm happy to do a Kahoot if you want. Okay. All right. Good week. Keep up with the homework. I'll send it later today. Again, this topic is a little bit hard. I don't think it's too crazy, but you got to be consistent. But with your schedule, manage that thing. I'm sure you'll do well, right? And just for the study skills, we're doing it very gradually, but that also means you can't leave things behind. You can't just be like, oh, I'm doing procrastination this week. I'm going to forget about scheduling, right? Everything we learn, incorporate it into a system. And then when the system might get too overwhelming, let me know. We can simplify things down to have everything in a more manageable way, right? So it's essential. You can't rush and like skip, pick and choose what you want to do. Slowly build out the system, okay? All right. Any other final questions? No, if not, I'll see you guys next week. Have a good one. Bye.